This video lecture is about the search for planets going around other stars outside the solar system, exoplanets, the characteristics of the planetary systems found so far, how we could find which planets might have life on them, and the search for extraterrestrial intelligent life.
The first six vocabulary terms focus on finding exoplanets from their gravitational effect on the easily seen object they orbit, the star. As an exoplanet orbits a star, the star's gravity pulls on the exoplanet, and the exoplanet's gravity pulls on the star by the same amount. Remember, the equal and opposite of Newton's third law of motion. Because the star is so much more massive than the exoplanet, the star has a smaller acceleration, and it is much closer to the balance point between them called the center of mass. The exoplanet is usually way too faint to see, so we'll analyze the star's light and look for periodic shifts in the star spectrum from the Doppler effect as the star orbits the center of mass. A blue shift as the star moves towards us, and a red shift as the star moves away from us. The last two vocabulary terms are other ways of detecting exoplanets indirectly from their effect on starlight. The transit technique has turned out to be the most prolific with the discovery of thousands of exoplanets. The method that was used first to find exoplanets orbiting other stars is the Doppler technique, also called the radial velocity method. Over 900 exoplanets have been found using this technique. This technique uses the fact that the exoplanet and the star both orbit a gravitational balance point between them called the center of mass. Because the center of mass is proportionally closer to the more massive object, the star has a proportionally smaller orbit around the center of mass than the much less massive exoplanet. We can't see the exoplanet, but we can certainly see the star. The star is going to appear to wobble back and forth. If the exoplanet's orbit is tipped to our line of sight, we'll see the star's spectral lines shift back and forth, shifted toward the bluer, shorter wavelengths as the star is moving toward us, and shifted toward the redder, longer wavelengths as the star is moving away from us. By the way, the exoplanet's motion is opposite the star's. So when the star is moving toward us, the exoplanet is moving away from us, and vice versa. If the star wobble is large enough, we may be able to actually see the star's position change on the sky. That is the astrometric technique, but it's really hard to see because our atmosphere blurs things so much. Only one exoplanet has been found using this technique so far. Both of these techniques rely on the gravitational tugging between the exoplanet and the star, so they are only able to detect the massive Jovian exoplanets because they have enough gravitational oomph to make their star wobble noticeably. That also means these techniques are going to be biased toward finding the massive Jovian exoplanet close to their parent star. Closer exoplanets will also have shorter orbital periods, so the star wobble happens quicker, making it quicker for us to see a periodic back and forth motion. We measure the orbit period and the star's velocity change. The orbit period gives us the orbit size, distance from the star, from Kepler's third law. Newton's form of Kepler's third law gives us the total combined mass of the star plus exoplanet. If we know the star's spectral type, we can estimate the star's mass, and we can estimate the exoplanet's velocity from the orbit size and period. This will enable us to derive the exoplanet's mass. However, since the measured star velocity from the Doppler effect is just the line of sight part of the motion, the radial velocity, the derived exoplanet's mass is just a lower limit. That is, the exoplanet could be more massive than what we derive from the Doppler technique. An exoplanet orbit tipped by a large amount, so it is more face-on, will produce a smaller Doppler shift. An exoplanet in a larger orbit causes a longer orbital period, from Kepler's third law. A larger orbit means a smaller velocity change because a smaller gravity force produces a smaller acceleration. A larger orbit will increase the size of the wobble, though, for the astrometric technique because the proportions of distances from the center of mass for the star and exoplanet depend on just the proportion of their masses. So, if the total distance between the star and exoplanet increases, the distance of the star from the center of mass increases. A more massive exoplanet causes no noticeable change in the period, since exoplanets are much less massive than stars. Remember way back in the gravity chapter when we talked about how things orbit, that all things at a given distance from a star will have the same orbital period. It's what explained the feeling of weightlessness, why the tiny Trojan asteroids have the same orbital period as huge Jupiter, etc. A more massive exoplanet will produce a larger velocity change in the star because a larger gravity force produces a larger acceleration. A more massive exoplanet also increases the size of the wobble for the astrometric technique because the star is not as proportionally close to the center of mass as it would be if the exoplanet was less massive. The next easiest way is to look for exoplanets going in front of their stars and seeing how much of the star's light is blocked, plus measuring the time between successive eclipses or transits. This is called the transit technique, and it has turned out to be the most prolific method with over 3,800 exoplanets found from specially designed space telescopes. A large planet will block more of a star's light than will a small planet. We can derive the size of a planet from how much of the star's light is blocked, the depth of the transit. The orbit size can be derived from the period of the transits, which is the time between the transits. We measure at least 3 successive transits to be sure the star dimming is due to an orbiting planet and not some other random process. The transit technique can detect both the large Jovian exoplanets and the small terrestrial exoplanets, but it does require near-perfect alignment of the exoplanet's orbit to our line of sight. This technique is biased toward finding large Jovian planets close to the star. They'll create bigger dips in brightness and more frequent transits. In addition to the planet's diameter and the orbit size from the orbit period, it is also possible to get the spectrum of the exoplanet's atmosphere, which could tell us the composition of its atmosphere. If we are able to measure the Doppler shift velocity change of the star, we can derive the true total mass of the planet because the orbit is nearly perfectly aligned with our line of sight. Putting the planet's diameter and mass together gives us the density, which indicates the overall composition of the exoplanet. The Kepler and TESS space telescope missions use the transit technique, and because they are above the distortion of the atmosphere, they could detect exoplanets even smaller than the Earth. But this technique does require staring nonstop for months to years at over 100,000 stars to find the chance alignments and transits that last for just a few hours. The microlensing technique uses the lensing effect predicted by Einstein's theory of general relativity that says that objects warp the space near them, so light passing near the object will be bent toward the object. 130 exoplanets have been found so far using this technique. The space around this object can then act like a lens. If one star passes in front of a more distant star, the distant star's light can be magnified by the foreground, closer star's warped space-time, by the closer star's gravity. As the closer star moves in front of the more distant star, you will see a rise in the brightness of the more distant star. As the closer star moves away from the more distant star, you will see a drop in the brightness of the more distant star. This takes place over several weeks to a few months' time. The animation shows what you'd see of the lensing if you had a super ultra-high resolution and the stars were close to us. Of course, that's not the case, and everything is all smeared out into one tiny dot. If the closer star has an exoplanet orbiting it that has an orbit aligned such that the exoplanet also goes in front of the more distant star, you can see a bump up, a spike or two, in the underlying rise or fall of the closer star's effect. How the distant star's light brightness changes can tell us the exoplanet's mass and orbit size. This technique can find both large Jovian and the small terrestrial planets near their parent star, but only if the closer star is dim, so it doesn't wash out the light from the brighter, more distant star. It also means we're looking for exoplanets around distant stars that are lensing even more distant stars' light. Like the transit method, a lot of stars, hundreds of thousands to millions of stars, must be monitored to pick up even a single stellar microlens event. The microlens events are due to chance alignments that are not repeatable. So the technique is good for helping us build up statistics of general properties of planetary systems, rather than giving us a lot of details about a single particular system. For those who prefer seeing something directly to believe it, there's the direct imaging technique, which looks for very faint exoplanets orbiting much brighter stars. 60 exoplanets have been found so far through direct imaging. In the visible wavelengths band, a star will be 1 billion to 10 billion times brighter than the exoplanet, but in the infrared, the star is much dimmer, and the exoplanet is at its brightest in the infrared, so the contrast ratio between the star and planet is only 10,000 to 100,000 to 1. The star's still bright, but much less so. You can use a device called a coronagraph, or star shade, to block or cancel out the light from the star, so you can see the dim exoplanet. This technique can find Jovian planets far from their parent star. It is possible to get the spectrum of the exoplanet's atmosphere using this technique. These are the 4 main ways of finding exoplanets, but there are other ways of finding exoplanets as listed in this graph. The transit technique brought in thousands of exoplanets when the data from the Kepler spacecraft was analyzed starting in 2013. Those are the green bars. The TESS spacecraft is finding many more, so the bars are going to get a lot taller.